All right, AP Chemistry class. This is your review for Unit 2, Molecular and Covalent Bonds, or they call molecular covalent and ionic bonds. The AP calls them molecular ionic bonds. And this material was covered largely in the video from Unit 1, the hour and 16-minute PowerPoint. I would recommend you watch that maybe more than once. It has a lot of facts and information and terminology you have to know. This is a bit of a review, but there is some new information. So I'm going to get through the first half of this a little bit quicker because you have covered it if you've watched that video. And even if you haven't, go ahead and watch this. All right, so here we go. So chemical bonds are the way that atoms are joined together to form millions of substances that we find in the universe. Amazingly, there are only 3 different ways that atoms do this: ionic bonds, covalent bonds, and metallic bonds. Bonds form because the bonded atoms reach a more favorable energy state. That's a phrase you should remember. Almost anything in chemistry happens for 2 reasons. Because positive attracts negative, that's called Coulombic attractions. Or it could be negative repels negative, like 2 electrons, and that's called Coulombic repulsion. You should get used to that term. The other thing is that because a chemical system reaches a more favorable energy state. Generally speaking, it reaches a lower energy. That's not always true, but the word favorable energy state is a catch-all. So, but it's generally lower energy. And that this means they have lower energy than the separate atoms. Again, that's not 100% true, but favorable energy state covers any situation where a chemical bond would occur. We will examine bond energetics in a later unit. So, ionic bonds. Ionic bonds occur when an atom with a low ionization energy, a weak guy, gives up an electron to an atom with a high electron affinity, a strong guy. Low ionization atoms exist on the left side of the periodic table and in the center of the periodic table. So that would be the alkaline earth metals, as well as the transition metals. Among these are lithium, beryllium, sodium, magnesium, potassium, calcium. Because these elements can most easily fulfill the octet rule by losing 1, if it's an alkali metal, or 2 alkaline earth metal electrons, 1 or 2 electrons, they easily give up their electrons. Remember, they want to be like the nearest noble gas, and for them to do that, it's easier for them to go backwards on the periodic table and up to the next row above than to go forwards over to the noble gas at the end of their own row. Nonmetals have high electron affinities, meaning they like to pull in outside electrons. Okay, so elements such as nitrogen, oxygen, fluorine, sulfur, and chlorine want to accept 2 electrons if they're in the oxygen group, or 1 electron if they're in the halogens, that's the second to last column in the periodic table, to fulfill their octet. So that will make them like the nearest noble gas, the one at the end of their own row. As a result, when a nonmetal and metal, especially alkali or alkaline earth metal, come together, then the metal passes an electron to the nonmetal. This makes the metal a cation, positive, because it has more positive than negative charge, because it's lost an electron, and the nonmetal an anion, negative, because it's gained an electron, it's gained a negative charge. Next, these 2 charged atoms are attracted together to form an ionic bond. So here's the example you saw in the video. So sodium has a low ionization energy. It's a weak guy. And it easily gives up its valence electron. That would be the star. If the sodium atom below can give away its electron, then its 3rd orbital disappears. It no longer has anything in the 3rd orbital. And the 2nd orbital becomes the valence orbital, which is full. It has 8 electrons in it. Chlorine has a high electron affinity. It's a strong guy. It likes to pull in electrons. If this atom can pull in 1 electron, the star, it can fill its valence orbital, which in its case would be the 3rd orbital, and it will be happy and have a full octet. The star electron has been passed from the sodium to the chlorine. Both atoms have full octets, so they're both happy. The chlorine has a negative charge because it now has 1 more electron than proton, so it's a Cl minus anion. The sodium has a positive charge because it has one less electron than proton, so it's a sodium plus cation. Because a positive charge attracts a negative charge, these two ions come together to form an ionic bond. Sodium chloride forms table salt. Sodium chloride forms table salt. It has the chemical formula NaCl. NaCl is called a unit cell or formula unit, but it is not a molecule. We'll talk about molecules, which are actually separate structures when we get to covalent bonding. So ionic bonds form crystal lattice structures as shown on the right. In crystal lattice structures, the atoms are like bricks in a wall or apartments in an apartment building. Each chlorine is surrounded by 4 sodium atoms, as you'll see in the diagram, and each sodium is surrounded by 4 chlorine atoms. No one sodium can say it belongs to any one chlorine and vice versa. So each NaCl is not an independent unit, but it's the smallest complete unit of the larger structure. So there's a one-to-one relationship between Na and Cl. Yet if you look at any one of those green Cl ions there, it's surrounded by 4 sodiums. So which one does it belong to? It doesn't belong to any one in particular. Again, it's forming like a brick in the wall. So you can tell one formula unit, one NaCl from the next. However, it's like bricks in a wall. No one Cl belongs to any one Na, but what NaCl, that chemical formula, is telling you is that there's 1 sodium for every 1 chlorine. And yet the NaCl is not a separate independent structure. No pair of Nas and Cls in that structure you see can just suddenly go off by themselves. Okay, covalent bonds. Covalent bonds are formed between 2 atoms with high electron affinity and high ionization energies. These are 2 strong guys. These two strong guys like to pull in electrons from other atoms, but they don't like to give up their own. So they're very good at holding on to their own electrons, but they also like to pull in electrons from other atoms. So they're strong guys. If you have a tug of war between 2 strong guys for the electrons, let me correct that. For the electrons of the other guy, then neither one is going to win. So if you look here, you have an oxygen, which has 6 valence electrons, and the 2 that you're interested in are the ones that are not paired. They don't have a second electron next to them. So you can see they have 2 empty spaces in the oxygen. The same is true with hydrogen. Hydrogen has 1 valence electron. It would like to have 2. Hydrogen and helium can only have 2. So what they can do is help each other to fulfill the octet rule by the 2 hydrogen atoms each moving over to join up with the oxygen. So in the covalent bond above, oxygen shares one of its unpaired electrons with the hydrogen and the other unpaired electron with another hydrogen. Similarly, each hydrogen shares its unpaired electron with the oxygen. These pairings are shown in the dashed ovals below. In each set of paired electrons, one of the electrons was contributed by the oxygen and one by the hydrogen. These shared electrons count as valence electrons for both hydrogen and oxygen, so you can double count them. They count as for both hydrogens. Let's go ahead and take a look at that. There you can see what it's referring to in the dashed oval. So those electrons in the dashed ovals there count for both the hydrogen, so it counts for 2 for the hydrogen, counts for 2 for the oxygen. So oxygen has 8 electrons in its outer orbital, that's octet, and hydrogen has 2 in its outer orbital, that for hydrogen, that counts as an octet, and so that's what that looks like. In each set of paired electrons, one of the electrons was contributed by oxygen, one by hydrogen. These shared electrons count as valence electrons for both hydrogen and oxygen. So we can see that oxygen has 8 valence electrons and is happy. Each hydrogen has 2 valence electrons, that is, all That's all the first orbital can hold, and it's happy. Please don't use the word happy on the AP exam. Again, use a phrase like it's energetically more favorable for the atoms to join together in that way. Energetically more favorable. Covalent bonds occur between two nonmetals because both are strong guys. Neither of these strong guys can win the tug of war and take an electron from the other, so they call it a draw, and they share the electrons. So that's why there's not an electron passed from one to the other, because neither one can actually take the electrons away from the other. Now, covalent bonds form independent structures called molecules. So let's look at molecules versus crystal lattice structure for ionic bonds. Molecules are independent structures that can be separated from one another. When water is boiled, the water molecules separate and float away. Ionic bonds form large structures of atoms that cannot be separated into independent structures. They can be ionized, but the NaCl doesn't break up in the water as NaCl in salt. It'll break up into Na ions and chlorine ions. It will no longer be NaCl. Think of water molecules as separate houses that stand separate from each other, or actually think of them like cars. They're separate independent objects that can move around on their own. Think of unit cells as crystal lattice structure as apartments in a large apartment building. The building is made up of units called apartments, and you can tell one apartment from the next, but no one apartment can be separated from the building. So the apartment building is like a crystal lattice structure. It is made up of units called apartments. Each apartment is a separate unit, but cannot be separated from the building. These cars are like molecules, and they are separate structures and can move separately. Okay, representations of covalent bonds. There are 5 ways that covalent bonded molecules can be represented. So here's an example of methane CH4. So the Lewis dot structure is the one we're going to use the most. The structural model we'll also use a lot, and that shows the electron pairs as straight lines. So each straight line represents a pair of electrons. Next is the ball and stick model that shows the atoms as balls and the bonds as sticks. Next is the perspective model. It shows bonds parallel to the page as regular lines, bonds coming out of the page toward you as widening lines, and the bonds receding back into the page going away from you as dashed lines. So that's the perspective model. And finally is the space-filling model. That's not used quite as much, but that gives you a sense of how large each of the atoms is and what area that its electron cloud will cover. Okay, double and triple bonds. Oxygen forms diatomic molecules. This means that oxygen pairs with another oxygen to form O2. Both of the oxygen atoms want to fulfill the octet rule and have 8 electrons. But how can they do this? Since they each have only 6 valence electrons. So 6 plus 6 is 12. So how do they form 2 octets of 8? 8 plus 8 would be 16. How do they do that? The 2 unpaired valence electrons in each atom form a double bond. Some atoms form triple bonds with 6 shared electrons, but not in the case of oxygen. In the diagram below, the electrons between the oxygen atoms are called bonding electrons. The valence electrons that are to the side and are not involved in bonding are called non-bonding or lone pair electrons. So let's go down and take a look at that. So there's oxygen. You can see that the separate oxygen atoms have 6 valence electrons each. The only way they can form an octet is to share not 1 pair of electrons, but 2 pairs of electrons. And so now if you see the oxygen molecule, the O2 molecule bonded, you can see that as long as you count those 4 electrons inside of that rectangle for each of the oxygens, then each oxygen will have 8 electrons in its valence orbital. The Lewis dot structure for the oxygen molecule O2 looks like that down below. A pair of bonding electrons can be shown as lines between the atoms. One line represents 2 bonding electrons. The Lewis dot structure for O2 can be shown as followed. By the way, lone pair electrons, you cannot use a line for lone pair electrons. That's why you see lines for the bonding pairs of electrons, but not for the lone pairs on the outside. And it says that right there. Only bonding electrons are shown as lines. Non-bonding electrons are never shown as lines. Okay, polar covalent bonds. Polar covalent bonds produce molecules that are electrically neutral, the same number of protons as electrons, but have one side that is more negative and another side that is more positive. This happens because the two elements have different electronegativities, which causes the electrons to be pulled more to one side of the molecule. In other words, towards the atom that's the more electronegative. It's going to pull harder on the electrons. In this case, O2, in the case of the O2, the bond exists between two identical atoms with the same electronegativity. This means that the electrons are evenly distributed so that there's no negative or positive side. This means that O2 is a nonpolar molecule. Water is a polar molecule. The delta minus and delta S, that's the Greek letters that you're seeing there. The symbols delta minus and delta S denote the more negative side and the more positive side of the water molecule. For reasons we will study later, there's a 104.5 degree angle between hydrogen atoms in a water molecule. So the oxygen is more electronegative than hydrogen. It's not electronegative enough to totally take hydrogen's electrons away from it, but it does tend to pull all of the electrons towards it. So oxygen tends to kind of pull all the electrons in that molecule towards it. That means the oxygen side of a water molecule is the negative side. It's negative. It's a more negative side, and the hydrogen side, which is having its electrons kind of pulled away from it, is a more positive side. So that's a polar molecule. So polar molecules will occur when you have a molecule between two different elements, which almost always means that one of them will be more electronegative than the other. Oxygen has an electronegativity of 3.5, while hydrogen has an electronegativity of 2.1. The difference between electronegativity of oxygen and hydrogen is 3.5 minus 2.1, which is 1.4. This would characterize water as a polar covalent molecule. Now, this next concept is not one that was covered in the video from Unit 1. Generally, atomic structures can be classified as nonpolar, polar, or ionic. So if the electronegativity difference between the two atoms is less than 0.4, some books will tell you 0.5. It's not, you don't have to worry too much about that. It's going to be nonpolar. In other words, there's not very much electronegativity difference, so the electrons aren't going to be pulled towards one of the atoms or the other very much. If it's between 0.4 and 1.8, it's polar. So it's not enough of a pull by one of them. So in this case, in the case of water would be an example of that. There's an electronegativity difference between oxygen and hydrogen of 1.4, so that falls in that range. So that means the electrons are going to be pulled mostly towards oxygen, but not enough so that you would call it an ionic bond. It's just they tend to be pulled more towards oxygen. So that would be a polar covalent molecule. Finally, if it's greater than 1.8, it's ionic. That means the electron is being totally pulled towards the more electronegative. So that would be sodium chloride. Chlorine has a much higher electronegativity than sodium, so it totally takes the electron away from sodium, and that's considered to be an ionic bond. This means that, continuing to read, this means that the electrons in a water molecule are pulled toward the oxygen side of the molecule, making the oxygen side more negative and the hydrogen side more positive. Okay, and there's a video that you can watch that'll go over this. Okay, I'm going to continue on with the text here. So metallic bonds. We don't deal with metallic bonds a whole lot in chemistry or in AP chemistry because they just kind of sit there. They form metals. Not a lot changes in metals. There's not a lot of chemical changes that are going on in metals, at least at this level of chemistry. So metallic bonds are found between metals. Metals have loose valence electrons in the third, fourth, fifth orbitals, or even below that. The many atoms in a metal can be thought of as sharing one big valence orbital. The valence electrons easily jump from one atom to another. This jumping creates many temporary positive-negative polarities between the atoms that causes them to bond. The figure on the right shows this effect. A video of metallic bonding can be seen below, so you can go ahead and link to that video or copy and paste that, or just copy that into a web browser. By the way, so you will have a copy of these notes that you can just copy and paste that or link to that, and they'll be in this same unit. Okay, so in other words, the electrons are not jumping permanently from one atom to the other like they would an ionic bond. They're just constantly jumping around. They're loosely held. They're almost as attracted, or they are as attracted to the atom. Say this is copper, for example. They're attracted to the copper atom next to them as they are to their own copper atom, and so they keep jumping around in between atoms. So they don't stay permanently with any one atom. And that's called the electron sea model, because the electrons swim around like fish in the sea. There's just a big ocean of atoms, and they can kind of swim freely around. Okay, the next concept is really important, and we're going to use it a lot. It's how do you draw Lewis structures for molecules. Now, the rules may not make total sense at first, but when you see it done and you practice it about 4 or 5 times, they'll make sense. So first, you determine the total number. You take the elements, the atoms, and the number of atoms that you're going to use in your molecule, and you determine the total number of valence electrons. You just count them up. Then you draw the structure. And first, the least electronegative atom occupies the center of the molecule and is usually written first in the formula. It's not always true, but generally true. B, hydrogen and fluorine occupy outside, called terminal positions. The reason for that is hydrogen can only form one bond, so it cannot be a central atom. It can't have a bunch of other atoms around it. It can only have one bond, so it has to be on the outside. Fluorine is the most electronegative of all the elements, so since you're going to put the least electronegative in the middle, that's never going to be fluorine. C, connect the outside atoms with the central atom using single bonds. That would be one pair of electrons, 2 electrons for each of those bonds. Then 3, place the remaining electrons to create octets. And you do that really around the outside atoms first. 4, place lone pair electrons around the outside atoms to give an octet. 8 electrons, hydrogen gets 2. 5, assign remaining electrons as lone pairs around the central atom. And finally, 6, form multiple bonds with the central atom if necessary. So for CH4, we'll show an example of methane. So carbon has 1 times 4 valence electrons, and you can know that just by looking at the periodic table. Carbon is the 4th element to the right in the 2nd row, so that means it has 4 valence electrons. Hydrogen, there are 4 of them, and each one has 1 valence electron. So you add that's 4, so you add 4 plus 4, and you get 8 total valence electrons for 1 carbon and 4 hydrogen. Step 2, connect the single bonds with hydrogen on the outside. Then so with the 8 valence electrons, each hydrogen has a full octet that has 2 valence electrons, and carbon also has a full octet with 8. So therefore, that's complete structure. You didn't have to go to any of the other steps. This was a very simple one. So everybody there has an octet, and you've used all 8 electrons. Those are the 2 things you have to satisfy, the 2 conditions. You have to use all of your valence electrons, and everybody has to have an octet. Let's do another example. Hydrogen cyanide Hcn. So you have 1 hydrogen with 1 electron, 1 valence electron. You have 1 carbon with 4 valence electrons. You have 1 nitrogen with 5 valence electrons. If you add those up, that gives you 10 valence electrons. Okay, so step 2. Hydrogen is on the outside because it always is. It can never be a central atom. Carbon is less electronegative than nitrogen, so it's in the middle. So that's one of the reasons they write the chemical formula HCN, because it shows the order of the atoms. That's not always true, but sometimes it is. And you connect everything with single bonds. So you have the hydrogen and the carbon connected with single bond. You have the nitrogen and the carbon connected with single bonds. Now the remaining electrons create an octet around the nitrogen. So you can see that nitrogen has 8 electrons around it. But carbon does not have an octet. So we must figure out a way. First of all, you have the correct number of electrons. You have 10 electrons in that first diagram you see there. So you don't want to add or subtract electrons. So in order to give carbon an octet, you're going to have to rearrange the electrons. In other words, you erase some of them around nitrogen and somehow put them next to carbon. And sometimes it's a little bit of like doing a puzzle. You kind of have to think about it and play around and see how you get it to fit. But you can see the solution right there. If you form a triple bond between carbon and nitrogen, again, all 6 of those electrons in the triple bond count both for nitrogen and they count for carbon. So nitrogen has 8 valence electrons, carbon has 8 valence electrons, and hydrogen has its 2 valence electrons. So that does fulfill the octet rule for all 3 of the elements. So you've done the 2 things you need to do. You've used all 10 of your valence electrons that you counted at the beginning, and you've created octets around all 3 of the elements. Let's do another example. Here's carbonic acid, H2CO. So you have 2 hydrogen and 1 electron, valence electron for each. That's 2 valence electrons. Carbon has 4 valence electrons. Oxygen has 6. So you add that up, and you have 2 plus 4 plus 6 is 12 valence electrons. So step 2, place the hydrogen on the outside and the carbon in the center, because it is the least electronegative. It's less electronegative than oxygen. Create single bonds between the central carbon and the outside atoms. So you see the first diagram on the left in step 3 does that. Okay, so you've used 6 of the electrons, but you have to use all 12. So we use up the rest of them by surrounding the oxygen. It's an outside atom. Surround that with electrons so it has an octet. So now oxygen has an octet. Each of the hydrogens has an octet. That's 2 electrons for the hydrogens. But the carbon doesn't. The carbon only has 6 electrons. So count how many electrons you've used. You've used 12 electrons. That's how many you have to use. So you don't want to get rid of any electrons or add any more electrons, but you have to rearrange them somehow. So what you do is you take 2 of those lone pair electrons from oxygen and you stick them in between the carbon and the oxygen. So oxygen still has an octet. You haven't changed that. But what you have done is you've given carbon an octet. So now carbon has 8 valence electrons. Oxygen has 8 valence electrons because they're sharing those 4 that are in between them. And hydrogen has 2 each. And so you've satisfied the 2 conditions of a covalent bond. That you've used all 12 of your valence electrons and that everybody has an octet. Okay, let's talk about resonance structures. Resonance structures, if you followed these rules, sometimes you'll get more than one molecule that would meet all of the conditions. And those are called resonance structures. So resonance structures are 2 different versions of the same molecule that are equivalent. Take SO2. The Lewis structure can be written in either of the 2 ways below. The arrow indicates that these are resonance structures. So that's how you would officially designate a resonance structure. So you could either have, you're going to end up with a double bond between the sulfur and one of the oxygens. Which one? Well, it could be either one. It could be the one on the left, or it could be the one on the right. So that's how you would draw the resonance structures. Now the resonance structure is shown above as designated by dashed lines. So a double bond is stronger than a single bond. It's also shorter. So when you look at this actual one of these molecules in the real world, does it mean that one side has a stronger sulfur-oxygen bond than the other, and one side has a shorter bond length than the other? And the answer is no. In the real world, it would kind of share. It would kind of have, instead of a double bond on one side and a single bond on the other, it would have like 2 1.5 bonds. You can kind of think of it like that. And that's what the dashed line represents. It represents kind of a 1.5 bond. So the sulfur oxygen on the left has a 1.5 bond. The sulfur oxygen on the right has a 1.5 bond. So they are equal. So they're somewhere between a double bond and a single bond on each side, but they are equal. And that's the way you would show that. So the formal way of writing it is up above where you have the two different structures. But down below, it shows you kind of the way it is in the real world. 1.5 bonds between each of the sulfur and each of the oxygens. Double bonds hold atoms more tightly than single bonds, so double bonds are shorter than single bonds. In a resonance structure, the bonds are somewhere in between the length of a single and double bond. In the SO2 bond above, the bonds between sulfur and each of the oxygen atoms is in between single and double bonds. As I say, like a 1.5 bond. Resonance structures mean that there are more than one structure that are equally possible. These are called equivalent structures. Now, formal charge. When molecules have two different structures, formal charge is a method of determining which of the structures is more stable. The structure with the formal charge that is closest to zero is the more stable and will be the structure found in nature. So I'm going to show you how to calculate formal charge. To calculate formal charge, use the following formula. The number of valence electrons in a single atom minus the number of lone pair electrons for that atom minus half the number of bonding electrons. So, in other words, you're going to have to figure the formal charge for each of the elements in a molecule. So let's take a look here. It's a little bit of math, but it's easy math. So let's take a look at CCl2O. And what you see here is, if you followed the rules for making the Lewis structure for this compound, you could either end up with the double bond being between the carbon and the oxygen, or you could end up with the double bond being between the carbon and the chlorine. So which is it? Which one of these two molecular structures does nature favor? It favors one of them. One of them is more energetically favorable in nature. And so formal charge is a way to calculate that. As I say, it's a lot of arithmetic, but it's easy arithmetic. So what we're going to do is for the one on the left, we're going to compute the formal charge of each of the atoms, not for the whole molecule as a whole. Well, eventually it is, but for each of the atoms individually. So look at the one on the left. The carbon has 4. So let's go back to the formula. Number of valence electrons in a single atom. So carbon has 4 valence electrons. A single carbon atom has 4 valence electrons. We know that already. Okay, next in the formula is minus the number of lone pair electrons. So carbon has 4 valence electrons. It doesn't have any lone pairs. Again, we're looking at the structure on the left. It has no lone pairs, so minus 0. And then half of the bonding electrons. So you can see that that carbon has a double bond. That would be 4 bonding electrons, a single bond with one of the chlorines and a single bond with the other. So it has a total of 8 bonding electrons. So you take 8 and you multiply that by 1/2, you get 4. So 4 minus 0 minus 4 equals 0. Okay, so for carbon, the formal charge is 0. Now, oxygen. Okay, so oxygen has a total of 6 valence electrons. Before it's even bonded with anything, it has 6 valence electrons. You subtract the number of lone pair electrons, so you can see that oxygen has 4 lone pair electrons there, the one on the left, and then half of the bonding electrons. So the bonding electrons between oxygen and carbon, there's 2 lines. That means there's 4 bonding electrons. So you take half that number, that's 2. So 6 minus 4 minus 2 equals 0. So far we have 0 and 0. Now the chlorines. The chlorines are both identical, so you can just calculate them both at the same time, but you have to double count whatever number you come up with. So chlorine, if you look at it on the periodic table, has 7 valence electrons. If you look at each of those chlorines individually, each one has 6 lone pair electrons, and each one has 2 bonding electrons. The one straight line represents 2 electrons. So that you take half of 2. So it's 7 minus 6 minus 1 equals 0. So you can see that all 3 of those are 0. That means that would be a preferred structure in nature. because it's closest to 0. But let's look at the other structure first. Maybe that's going to be all zeros as well. So let's take a look at that. So carbon, let's take the carbon again. Now we're over on the right-hand structure, the right-hand side structure. Carbon has the 4 valence electrons. It doesn't have any lone pairs, and it has 8 bonding electrons because each of those lines represents 2 electrons. So that's half of 8. So 4 minus 0 minus 4 is 0. So it's exactly the same as the other side. Now oxygen. The oxygen in this structure has 6 valence electrons. You can count that it has 6 lone pair, and that it has 2 bonding electrons with the carbon. So you cut that 2 in half. You multiply that by a half, and you get 1. So it's 6 minus 1. So now we have a number that's not a 0. It's negative 1. And now we're going to do the 2 chlorines separately because they're not identical. Notice that one of them has a single bond with the carbon, and the other one has a double bond with the carbon. So let's do the one with a single bond. So it's chlorine has 7 valence electrons, 6 lone pairs in that chlorine that's up on the top, and then 2 bonding electrons, so you cut that in half, and that's 1. So it's 7 minus 6 minus 1 is 0. Finally, the chlorine with the double bond. It has 7 valence electrons. 4 of them are lone pair. You see 4 lone pairs on the chlorine on the right, and it has 4 bonding electrons, so you cut 4 in half to get 2. So 7 minus 4 minus 2 equals 1. So you can see that the chlorine, the molecule on the left, the CCl2O, has zeros for its formal charge, whereas the one on the right has a negative 1 and a positive 1. What that means that in nature would prefer the molecule on the left because it has the formal charge closest to 0. Notice that in both cases, if you add up the formal charges of each of the elements, you get 0 in both cases. That has to be true because this molecule doesn't have a charge. It's not an ionized molecule. We'll get to that later when that happens. But the formal charge it's a way to check your work. 0 plus minus 1 plus 0 plus 1 on the molecule on the right would be 0. So if you didn't get 0, it means you did your arithmetic wrong. Okay, let's keep going. This was kind of a long explanation. That's only because there's a lot of arithmetic. Okay, so because formal charges of a molecule on the left are 0, this is the more stable structure. Let's talk about compounds and molecules. There's a difference, and sometimes students get these confused. So a compound is a chemical structure made of 2 or more elements. So water, H2O, is a compound because it has hydrogen and it has oxygen. An oxygen molecule, which is O2, is not a compound. It's made of a single element. It is not considered to be a compound. A molecule is a structure made of covalently bonded atoms. So let me go to that example again. Water is both a compound and a molecule because it's 2 or more different elements and they are covalently bonded. Oxygen, O2, is a molecule. It's covalently bonded, but it's not a compound because it's not made of 2 or more elements. So keep those 2 definitions straight. A unit cell is the smallest part of an ionic or metallic structure that can create the structure when repeated. So think of the apartment building structure again. An apartment is not a separate structure from the overall apartment building. But if you took the design of one apartment and just kept repeating it over and over again, put them side by side and one on top of the other, you would have the entire apartment building. So it's made up of those little units called apartments. They all look the same. We're assuming this apartment building, they all look the same. And if you just keep putting them together side by side, one above the other, you have the apartment building. So even though the apartment is not a separate independent structure, it shows you the basic unit you need to build that apartment building. So let's continue with the reading. So take the following examples. O2, oxygen is covalently bonded, so it is a molecule but not a compound because there's only one element. H2O, water is covalently bonded and it has 2 different elements, so it is a molecule and a compound. And NaCl, sodium chloride, salt, is a unit cell. It's not a molecule. Again, it's like the apartment in the apartment building. of an ionic bond, meaning that you can create a large block of salt by repeating NaCl, 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 as you saw in the diagram a few pages back. So NaCl is a compound. It has two elements, but it's not a molecule. It's a formula unit or a unit cell. Exceptions to the octet rule. The exceptions to the octet rule occur for three reasons. 1. Atoms with an odd number of valence electrons, such as boron and nitrogen. So boron has 3 valence electrons, nitrogen has 5. So NO, there are 2 Lewis structures possible. In each case, one of the atoms does not have a full octet. So, and it tends to be nitrogen. Oh, no, I take that back. It's nitrogen in the first one and oxygen in the second. So notice that nitrogen in the first diagram there has 7 valence electrons, oxygen has 8. In the second diagram, nitrogen has 8, oxygen only has 7. So when you have an odd number, it's really hard to create octets because octets are 8, and multiples of 8 would be even numbers. Second, polyatomic, meaning many atoms, molecules with less than an octet. So an example is boron or aluminum. Boron only has 3 valence electrons, so it can really only bond on 3 sides. So you could have BH3, or you could have BF3, which you see here in this diagram. So you can see that the fluorines have full octets. They have 8 electrons each. But the boron, remember those lines represent 2 electrons, only has 6 valence electrons. So that is an exception to the octet rule. You don't try to find 2 more electrons. They just aren't there. Extended octets. They do not test this on the AP, but let me just mention it. Atoms in the third period row and below can have as many as 12 valence electrons. We will study these later. We really won't. They don't test them because the theory about extended octets is controversial in chemistry. It's not settled science, so they won't test you on this. But if you look at this, phosphorus can actually bond with 5 different chlorines. So you notice that the chlorines in that diagram all have 8 electrons around them. They have octets, but the phosphorus has 5 lines. So that's 5 times 2. That's 10 electrons, 10 valence electrons for phosphorus. And as I say, there's other compounds that can have 6. They can have 6 valence electrons and 6 different atoms around them. Okay. Number of bonds, bond enthalpy, and bond length. Example, carbon. Carbon can form single, double, or triple bonds. As number of bonds increases, the bond enthalpy, that is the energy required to break the bond, and we talked about that in class, but we haven't gotten to it yet in review. Remember, enthalpy is heat. It's the energy that goes into or out of a chemical reaction or a chemical compound when you either form the compound or break the bonds in the compound. So when the bonds form, energy is released. When the bonds are broken, you have to put energy in. Think about it. If you break a pencil, you have to put energy into that pencil to break the pencil. So carbon can form single, double, or triple bonds, as you see in those 3 diagrams. And I didn't read B. B, bond length. The distance between atoms decreases. Okay, so the energy required to break a triple bond is greater than the energy required to break a single bond. And the length between the 2 carbon atoms with a triple bond is shorter. You might think it would be longer because there's more electrons in between them, but that's not true. It's shorter. So triple bonds are shorter, and we'll talk about where those extra electrons really are in a later lesson. And finally, dipole moment. Dipole moment is kind of a combination between how long the bond length is and how polar it is, how much the electrons are pulled to one side. So the longer the bond length and the more polar would be a greater dipole moment. What it means is that the charge is really great, the charge difference between the 2 atoms is really great, and they're really separated by a long distance, by a far distance. So longer bond length and greater polarity or polar difference or electronegativity difference between the 2 atoms will produce a larger dipole moment. You do not need to calculate this on the test. There is a calculation for it. You don't need to do that. Just understand the concept. So when there is an unbalanced charge, such as a polar covalent bond, it creates a dipole. A measure that is useful to chemists, but that you will not be required to calculate, is called dipole moment. So the dipole moment is the magnitude, the amount of charge, in other words, charge separation, how much electronegativity difference, times the distance between the charges in the molecule. And it's given by the formula the dipole moment equals the magnitude, that's a fancy word for how big, the amount of charge, times r, that's kind of abbreviation for radius, the distance between the charges. And the dipole moment is measured in a unit called a debye. Okay, so that takes care of these notes. This was about 48 minutes. You can just read them if you want. I have these notes in there. If you want to go to those links, the YouTube videos are only about 2 minutes, and you can watch those YouTube videos. Again, the first half of these notes roughly were things that we studied yesterday. The second half, though, was all new material. So be sure you understand the concepts of resonance structures and formal charge, and I'm going to give you some problems to do that. And let's see, that last sentence is not really important. Okay, so we'll see you. Today is Wednesday, May the 6th that I'm recording this. We're about a day behind what the schedule says, but that's not a problem. We can keep up from now on. Okay, so take care, and I hope to see you on one of the Zoom calls. Bye-bye.